Assalamu alaikum wa rahmatullahi wa barakatuh. Bismillah ar-Rahman ar-Rahim. Inshallah, today we'll continue talking about loss functions, probably also for the next lecture. This session is really important. So I want you to really pay a lot of attention and make sure that you really understand the steps that we will go through. Last lecture, we started to think of changing our view of the output of any model. And instead of predicting the output right away, we want to predict a probability distribution over the possible values of the output. Right? Do you remember something like this? Depending on the type of the problem, we will choose a probability distribution. Either for continuous values, it will be something like normal. For discrete values, it will be something like Bernoulli or categorical. We'll talk about that. And then we assume that the model will actually predict that probability distribution instead of just one value. So you can think of it that way, that the model will assign a probability for each possible output. So for that value of the output, maybe this is 10%, the other is 40%, the other is 35%, and so on, instead of just giving one value. And this, as you will see, will make it easy for us to construct a loss function that is appropriate for that type of problems. So for every type of problem, as you see here, we might choose a different probability distribution. Here, this is a regression problem, so we choose a normal distribution. Here, this is a categorical distribution because the output is discrete. Another categorical distribution. Here, this is another continuous distribution also that is suitable for the output here, which is a direction. So the point here is that for every type of a problem, we might get a different, or we should choose a different probability distribution. Now, we said it very easy, right? We said that the model will predict a probability distribution. Now, what does that mean? How actually a model can predict a probability distribution? We know that in a neural network, the output nodes will produce numbers, right? Okay, so it won't be a probability distribution. So the trick here is very easy. We will have it in two steps. First, as we said, we will have to pick a known parametric distribution that is good for the output, or that can work over the output, the possible values of the output. First, what do we mean by parametric distribution? The word parametric, okay, what does that mean? It has parameters, okay, a distribution that has parameters. So we assume, of course, that the distribution has parameters, and here's an example. The normal distribution, of course, has two parameters, which are the mean and the variance. Right? So first step, pick specific probability distribution. How? Depending on, as we will see in the example, depending on the possible values of the output. Okay, whether they are continuous or discrete, that will make a difference. Then we set the model to predict the parameters of this probability distribution. So the model actually will not produce a distribution. The model will produce values that are the parameters of that distribution. So in that example, the model, the distribution that we selected is normal. So we will set the model to predict the mean and the variance of that model, of that distribution, sorry. Okay? And this is how we will make the model to predict a probability distribution. We'll pick one distribution, and then we will design the model, which is in our case what? In this course, what is the model? A neural network, right? So we will design the neural network so that the output will be the parameters of the probability distribution. Okay? We'll see that inshallah in detail. Now, as we said last time, we want the model to give high or low probabilities for the correct answers. High probabilities, right? We want the model to be accurate. Accurate means it is actually giving a high probability for the values that are the ground truth, the values that correct the correct output. So, for example, if this is the training data, let's say that we are back to the example of the height and age. Given the age I want of a child, I want to predict the height. Okay, so let's say that these are the pairs, the x and y over the examples, over the training examples. Okay, for each age, there is a height, right? Okay, and I want the model to predict those values. So let's say مثلا among the values here is when the age is 2.5 years, let's say مثلا the height will be 140 centimeters. Okay, so this is given in the training data, right? I want the model, when I give it 2.5 as an input, to give me a distribution where 140 has a high probability. Okay, so let's say that for that input, the model gave me a distribution like this. Of course, let's assume that for this problem, the normal distribution would be good distribution, and let's say that the center of, or the mean of that distribution was at 170. Okay, is that a correct or a good estimate? Why? What is too high? The 170. But what we look actually for is the probability of the correct answer. So the probability of the correct answer will be something like this, right? This is maybe here. This is 140, right? So this probability is high or low? Is low, relatively, right? So this is not a good. This is not a good model yet. Okay. So a model that will give high probability here, something like this one, مثلا. Okay, if we have this distribution, then maybe the highest probability is 142, مثلا. Okay, so 140 will be still high. Okay, so we want, when we are training, we want when we are training, we want the model to assign high probabilities for the correct answers. Okay, the correct answers are here. What are, for a given xi, the correct answer is yi from the training data, right? Because we have pairs xy, xy, x1, x2, y2, y1, x2, y2, xi, yi. So for an input xi, I want the model to get, or to set, or to assign a high probability for yi. The model will be penalized as much as the probability is far from 1, because 1 is the maximum possible probability, right? Okay, so if it's close to 1, then the penalty will be very small. If it's very far from 1, like 0.1, then the penalty will be high. Okay, and that's exactly captured in this equation. Okay, let's think what is this. Here we are going over all the training examples. So this is a product, you know, this symbol for the product is from 1 to I. I capital is the number of the training examples. So this is going through all the training examples, multiplying the probability that given xi, I will get yi. So this is the probability of the probability that the model assign for the correct answer yi for the input xi. Okay, is that clear? So here x1, y1. So I want, from this will be probability of y1 given x1 times probability of y2 given x2 times the probability of y3 given x3, and so on. And I want actually to find the parameters of the model phi that maximize this product. Because if we maximize this product, that means that the model really assign high probabilities for the observed output, for the correct output. Are you following with me? Okay. And if we maximize this function, then we reach the model that we want to get eventually. So this is the process of training. We want to find phi. Okay, we want to find phi. Phi is what here? Phi are the parameters of the model, which are what? the weights and biases, okay, in our case. Okay, but by the way, in general, this lecture today is not only about neural networks. It's about any learning model. Okay, but in our case, the parameters, which are always denoted by phi in this course, the parameters of the model are the weights and the biases. Yes. The parameters will be learned using the training data. Okay, so phi is the parameters of the model, which are the weights and the biases. So we want, out of this equation now, we want to, so let me clean it up a bit. So we want to, just 1 second, we want to maximize, okay, we want to maximize the product of the probabilities that the model assign to the correct answers. Yes. Yeah, wait a second. Okay, that's why I'm asking you about phi in particular. Phi is the parameters of the model. We also talked about the parameters of the probability distribution. Okay, we call it theta. Okay, so theta is the parameters of the probability distribution. Now, since the output will depend on this probability distribution, which is a function of its parameters, then we can say we are maximizing the probability of yi given theta I. Okay, because this probability is the probability distribution over the possible values of the output, right? And the values of the output is function of theta I. Okay, so we can say that we are maximizing the probability of yi given theta I. It's not only xi, it's also the parameters of the probability distribution. Now, distinguish between two sets of parameters. Phi is the parameters of the model, which are the weights and the biases of the network, if we're talking about a neural network. And theta is the parameters, is a set of parameters of the probability distribution that the model will predict. Okay. Now, we said that for the model to predict a probability distribution, it will actually predict the parameters of the distribution, right? So actually, these parameters are the output of the model, right? Which is, remember the model always we call it f, right? So theta I actually is f of xi and phi, is the output of the model. So if I have a model like that, let's say مثلا we have x here, that's the input, and we have three, so we have three layers like that. This is the output of the model, right? We said that we will set the output of the model to predict, we set the model to predict the parameters. Okay, let's say that there is one parameter of the probability distribution, so this is theta. So this is, as a whole, the model is a mathematical function, if you remember, right? It's f of, it's a function of what? Of the input x and the parameters of the model, which is phi, exactly, which is the output. So that's theta. Okay, so theta I is f of xi and phi. Okay, you got that? Any question about this? Yes. Exactly. Yes. This is what we are saying here. So this is the output of the model now, right? So this is not directly the output that we want in the application in our problem. No, this will be now the one or more of the parameters of the probability distribution. So for every input x, we will predict a distribution. يعني if I give you مثلا, if they give the model the value 2.1, it will produce, let's say مثلا this distribution. That's 3. Okay. For another point, it will give a different distribution. For a third input, it will give a third distribution, and so on. For every input, it will give a distribution. This distribution is determined by its parameters, right? So we will set the model to predict these parameters. Once I know the values of the parameters, I know the distribution completely. Yes. Okay, very good. If theta is the output of the model, then what is yi? We thought that yi is the output of the model. Is yi the output of the model? It seems not, right? Because we have here yi and theta I. So what is the difference between yi and theta I? Yi is the correct answer from the training examples for xi. Okay, so this is xi, this is yi, but that's not now the output of the model. Okay, and we'll never, by the way, yani this is just the reference to us to see if the model will give us the correct answer or not. Okay, whatever the output, we will compare it with that observed value. But now we have the output to be theta. Why is it theta I, not theta? Because it's different for each training example. For every x, we'll have theta. So x1 have theta 1, x2 have theta 2. That's what the network will predict for that input. Okay, is that clear now? It's very important that this is, inshallah, to be clear. Okay, to make sure that you really understand the rest of the lecture. Okay, type. Why do we want to maximize actually? So what is the meaning of this? That means that we want to find the values of phi, which are what? Again, the model, the parameters of the model, weights and biases. That will make this function, this product, the maximum possible. That's why this equation is called maximum likelihood criterion. Okay, maximum likelihood. Likelihood of what? Likelihood of seeing the observed output. Okay, likelihood means probability, right? So I want to maximize the probability that the model will assign to the correct answers. Okay, so this is called maximum likelihood criterion. Okay, are you Fatima? Okay. Any questions? Is everything clear so far? Okay. Now, to do this, to have this maximum likelihood criterion, we actually have two assumptions. First is that for every input, we have the same type of the distribution. We have the same type of the probability distribution. So I cannot say, مثلا, that for x1, I will have normal distribution, but for x2, I will have Poisson distribution. No, we'll assume that all the distributions are the same. But of course, they have different parameters, right? For every input, we'll have different parameters, but they are the same. So the data are identically distributed, and also those probability distributions are also independent, which allow us to have this product this way. So this is actually the original, the exact, real probability that we want to maximize. The probability of y1 and y2 up to yi given x1 and x2 up to xi. But because we assume that the probability distributions are independent, so we can approximate this complex probability, very complex probability, to the product of the individual probabilities. Okay, so this is by the IID assumption, the identically and independent and identically distributed data. Okay, this assumption is used a lot in statistics and machine learning to make our life much easier when we do the calculations. Okay. Okay. Now back to the maximum likelihood criterion. So again, this is the likelihood function, Okay, we want to maximize it. We want actually to find the model parameters that will maximize it, which will be phi hat. Okay, now if you look at this function, the likelihood function it's now a product of probabilities, right? And we know that probabilities are between 0 and 1, and many of these probabilities might be very small. What happens when you multiply small numbers together? It will the output will be smaller. Okay, whenever you multiply by a number that's less than 1 and very small, it will get smaller and smaller and smaller. Maybe it will be very close to 0 if that the number of the multiplied factors are many. Okay, so that's a problem because we might not be able to represent that number actually accurately. We might get underflow. So we'll have to handle this, because if we really have this function to maximize, it will be, in practice, it will be almost 0, okay, when we compute it. So we'll have to solve this problem, and the solution is really easy. Using the log function. Remember the log function we talked about last time? You have a question? No, we will not be able to. Which parameters we change? That's not about changing the parameters. It's about the fact that these are probabilities, and many of them are very small, which means many of them are close to 0. When you multiply very small numbers like that, many of them, the product will be very, very close to 0. No, it means that because we did this assumption, the consequence of that is that these values will be always 0. Okay, so to solve this problem, we'll use the log function. Remember last time we said that the log function is monotonic. So whenever we increase the input, the log will increase. Okay, so let's assume that we have this function here, this function. Okay, so let me change this. So let's say that we have this function. Okay, and we take the log of that function. When we do that, we get this function. Okay, now the question is, are these two functions the same? No, of course. This is the original function. Oops, sorry. This is the original function, and this is the log of that function, right? But remember that if we want to maximize it, we'll find that the maximum value of this function, the maximum value of this function, okay, let me get back to the pen then. The maximum value of this function is at a specific value of the input, right? Which is, let's say, مثلا, this is, I don't know, -4. Okay? When we take the log of that function, the maximum of the new function will still be at the same point, which is -4. Okay? Although the function itself changed, but the value at which we get the maximum of that function will not change if we take the log. Okay? Is that clear? Right. Keep that in mind because we will use it in the next slide. Okay? So again, the message here is that if we have a function, the function will reach the maximum at specific value of the input. That specific value of the input will not change if we take the log of that function. Okay? Now, getting back to the original likelihood function, which is this. We want to maximize it, right? Right? And we want to find the value phi that will maximize it, right? If we take the log of that function, phi will be the same, right? This is exactly what we said last in the previous lecture, previous slide. Okay, so phi will still be the same if we take the log of that function. So now it's like instead of maximizing this function, we actually want to maximize the log of that function. Now when we take the log of a product, what happens? It's converted to summation. So now instead of having log of the product, we have the sum of the log of the individual values. Type how that solved the problem. Instead of multiplying very small numbers, we are just adding the log of them. Okay, so we'll not have this problem. And still we will have the same learned model, which is the parameters, right? We are trying to find the parameters that will maximize this or that, and they will be the same. Okay, is that clear? So now it is a sum of terms, so it doesn't matter so much if the terms are small, because we're just adding them. Okay, any questions so far? Yes. We can use this function in practice. Yes, because the values that we will get will not be very small, like the multiplication. Okay. So this is from the practical sense. Okay, so this function is called the likelihood function. This function now is called the log likelihood function, right? And these are the same, of course. These two are the same, okay? And this one, I mean, both are the log likelihood function, and this is the likelihood function before taking the log. This is just the terminology, okay? Type. Usually in optimization, and because we have a loss function, or we want to have a loss function, we don't want to maximize, right? We want to minimize a function, right? So instead of using the log likelihood function and maximize it, we can just take the negative of it and minimize it. So this is the log likelihood function that we saw in the previous slide. We just multiplied by -1. Now it's called negative log likelihood, and we minimize it, which is the same, like maximizing the log likelihood function. Okay, so maximizing the log likelihood is the same like minimizing the negative log likelihood. We are getting the same model parameters, the same values of the model, of the parameters of the model. Okay, these two equations are equivalent. When we maximize a function, we are actually also minimizing the negative of the function. It's the same. But in this case in particular, it's a loss function. So a loss function means we want to find a value that is small of, so we want to minimize it actually. Okay, so to call this is not a loss function. We cannot call it a loss function actually. It's the likelihood or log likelihood function. But now we can call this a loss function. Actually, this is the loss function. Okay, this is the loss function that we will use actually. So the loss function is the negative log likelihood, and we will minimize it now. Yes. Now, if we, okay, so let me ask you a question now. If you look at this function, what is needed to compute the loss? Well, and if I'm telling you now, this is the loss function, okay? And in training, we need to compute the loss function, the loss value, right? Remember the regression, we computed the loss for every point, right? For every model. For every model we train, we can compute the loss. Now, to compute the value out of this loss function, what do we need? We need to know these probabilities, right? We need to know these probabilities. And of course, we need to also to know these, the parameters of the model. We need to have the model, and we need to know the probabilities, right, from the distribution that the model will predict for this input, for every single input in the training data, right? Okay, did you agree with me that we want to maximize the probability that the model will assign to the correct answers, right? So when we maximize this function, that means that the model will be better, right? Okay, it is also equivalent to maximizing the log of that function, right? Right? It is equivalent to minimizing the negative of the log of that function. Okay, now this is minimizing a function. Okay, So now we can call this function a loss function because we are minimizing it. Okay, is that clear now? Okay. It's the same, yeah. It's just the mathematical manipulation. Okay, so that now we can have a function to minimize instead of maximize. But it's the same concept. Maximizing the likelihood is the same like maximizing the log likelihood. It's the same like minimizing the negative log likelihood. Okay, but the last one is the one that we call it loss because we want to minimize. Okay, we cannot call this loss. We cannot call this function loss because we want to actually have high values of it. Okay. Okay. Now let's assume that we found the model the good values for the model parameters. Okay. Type. I want to use this model in reality. In reality, we given in our classical example, given age, I want to get the height, right? But now we set the network to predict not the height, it predicts a probability distribution, right? So what should we do? Should we give the probability distribution to the user to say, okay, so what should we do? Yeah, so we have to get one number. Okay, so to get one number, I think the logical thing to do is to find the value that has the highest probability in that distribution, right? And that's exactly what we do in inference. So in inference, we need actually an actual prediction. We need just one point estimate that we can pass as the predicted value. So we will find the peak of the probability distribution, okay, the maximum value of the probability, and then assign the output to it, to the value that gave us this highest probability. So we will maximize the probability, which is coming from the probability distribution, from the distribution. Okay, so the value that will get the highest probability is the predicted value. Okay, but in our case, if we use the normal distribution, what will be the value that will give us the highest? Yes, the mean. Okay, it just happened that the mean will be the highest value in that case. And it happened that the mean is the one that we actually predicted from the model. Okay, just in that case. In other cases, might not be exactly the one the thing that we predicted from the model. Okay, but in general, we want the value that will give us the highest probability. That's the best we can do, right? You gave me a probability distribution. If I want just one value, then logical thing is to get the value that has the highest probability, right? So here, if we have the normal distribution, then of course y will be y hat in this case will be mu. Okay, questions? Okay, question from me. To construct a loss function, we set the model to predict input or output or probability distribution or parameters of a probability distribution. We set the model to predict what? The model. Okay. Do we set the model to predict the output directly? How about the input first? Of course, we don't predict the input, right? We predict. We don't predict the output directly. Okay. To construct the loss function, we don't predict the output directly. We predict the probability distribution or the parameters. Both are correct. Okay. Actually, we to predict the probability distribution, we predict the parameters. So both are correct. Okay, but not the input, of course, and not directly the output. Okay, any question about this these answers? Type another question. I want you to really think about it. Okay, in training a model, we maximize the likelihood or minimize the likelihood or maximize the log likelihood, minimize the log likelihood, maximize the negative log likelihood or minimize the negative log likelihood. Okay, think before you answer, please. So do you have one answer only or more? Let's take it one by one. Is it maximize maximize the likelihood? Huh? We really want to maximize the likelihood probability? Huh? Yes or no? Why no? That's why this is actually what we want. We want to maximize the likelihood. This is what we started the lecture with, right? That's our goal. So our goal is to maximize the likelihood, right? Right? Type. So that means that minimize the likelihood is wrong, right? Okay. Type. Maximize the log likelihood. Yes, it's the same like maximizing the likelihood. Type. Minimize. No. Type. Maximize the negative log likelihood. No. Minimize. Yes. So this is also okay. Is that clear now? So all of these three will give us the same thing. But mathematically, we will use minimize the negative log likelihood because now we can call it the loss function. Okay? Yes. Yes. No, no. Log likelihood doesn't have negative. It's just the log. And the log, if so, taking the log will not change the sign. Okay? I mean, it will give us, if we the maximum of both functions, the original and the log, will be at the same point. Will be at the same input. We don't care. Okay, that's a good question. Okay? And let's get back to here. Okay. Yes, this one. This one. Now, this is the likelihood, right? Okay, we want to maximize it. Okay? Right. Do we care maximize it to get what? What's the goal of maximizing this function? To get the values of the model that will get that maximum, right? So do we care about the value of the maximum itself? We don't care. We don't care. That's why we don't care if we take the log. Yes, taking the log here will give us different loss values, by the way. This function is different than this, right? They are different. They will give us different values. The loss, the value of the loss of whatever, not the loss, sorry, the value of the function of this function will be different than the values of this function. But we don't care. Okay, we care about the value of phi that will give us this maximum. That's this maxima. Okay, and they will be at the same point. Same here. Okay, we don't care about the value of the loss function. We care about which value of the parameters that will give us that value. Of course, we want to minimize it over time. Okay, but the absolute value will be different from here to there. Okay, is that clear now? Any questions before we continue? Okay, now we need to have a recipe for loss functions, recipe for constructing loss functions. What do you think out of our discussion so far? What are the steps that we need to do? What is the very first step? Yes, so the first thing is to choose a reasonable probability distribution for that type of a problem. So given a problem, we need to think about what is the output of that that we need from the model that we want, and based on that, we choose a suitable probability distribution. Then, now after we select the probability distribution, we said that we will do something with the model, with the network itself. Yeah, we set the output of the model to be one or more of these of the parameters of the probability distribution. And if we pick the normal distribution, we have mu and sigma square, right? The mean and variance. Okay. Then now the output of the model will not be the actual output, the real output, will be one or more of these parameters. Okay. So that's the second step. And then we minimize by the loss function. Now we have the probability distribution. We can have the negative log likelihood, which is the loss function. Okay, so we will minimize it, and that's the talk bench of the next session. And then the fourth, after we train, the model. To do inference, we need to pick the value that has the maximum probability. Given an input, we have a probability distribution as an output, we pick the value that has the maximum probability. Okay, these are 4 steps. We'll go through them for, I think, 3 or 4 examples, okay, so that you really understand this process. So first, we choose a suitable probability distribution that is defined over the domain of the output. So we need to think about what is the domain, what is the range of the possible values of the output, whether they are discrete or continuous, and so on. And then we set the model to predict one or more of those parameters of that distribution. Then to train the model, we need to find the optimal values that will minimize the loss function. Okay, and the loss function is the negative log likelihood function. And we do that over all training examples, of course. Okay, we do this computation over all training examples. And finally, to do inference, we for a test example, we get the value that will maximize the distribution, the output distribution. Now let's do that over multiple examples. Okay, we'll start with the univariate regression, and I think we saw this example application before. Given some information about the house, we want to estimate the price of that house. Okay, why is that a regression problem? The output is continuous, right? The output is continuous. Type, what could be a good probability distribution for that output? Gaussian distribution, okay, or normal distribution. Okay, so normal distribution will be good here. So that's the first step, is to select the probability distribution. For that, the normal distribution will be good. Type, the normal distribution has 2 parameters, the mean and the variance. And with different values of the mean and the variance, of course, we will have different shapes of the bell curve, right? So here, the mean, this is the mean, and the variance is small or high? Small, right? When the variance is really large or high, you will see that the bell shape is flattened. So this is the example of a higher variance than this, and actually this is also higher variance than the other two. Okay, so the shape of the bell shape will depend, of course, on both the mean, which is the center of the shape or the curve, and the variance, which is how it indicates the width of the shape. Yes. Depending on the domain of the output. Of course, there are many distributions, so you can pick one that is that can be defined over the domain of the output. So here, the domain of the output is the real numbers. Okay, so normal distribution is one candidate. If there is another distribution that is also defined over a continuous domain, then you can use it, of course. Okay? But if the knowledge, it also depends, or you should factor in the knowledge of the application itself. Okay, and sometimes you will see that there are some restrictions about the output that will make you focus on specific type of distributions. Okay, we'll see over the examples. Right. Okay, now picking a distribution means that now we can see the actual probability density function. Okay, remember this from statistics class? This is the probability density function of the normal distribution. Okay, given any value, we want to get the probability of it, we just plug it in the function, the density function. Okay, as you see here, the density function is function of the 2 parameters of the normal distribution, which is mu and sigma square, the mean and the variance. If I know the mean and the variance, given any input, I can compute the probability of that value. Okay. Type. Second step. We need to set the output, set the model to predict one of these parameters or more. Okay. So we will assume here that we want to predict mu, which is the mean. So we pick the normal distribution. Okay. Once we pick a distribution, we want to predict its parameters. We want to make the model predicting its parameters, not the actual output, the parameters of the probability distribution that we picked. Okay, we can either predict one of these parameters and assume that the others are constant, which is the case that we will start with, or we can assume that we don't know any of the any of the parameters, so we will predict all of them. Okay, so we'll start with the first case, which is we want to predict one of them, and the other will assume that it is a constant. Okay, so that means that now mu, which is one of the parameters, will be the output of the model, right? Remember, the output of the model is f of x and phi, right? Again, what is phi? Parameters of, or the probability distribution, the model, which are the weights and biases. So then what are the parameters of the distribution? In this case, they are mean and variance. In our terminology, it is theta. Okay, just to make sure that you are following with me. Okay, so now we can plug in the expression, the probability distribution expression. Okay, instead of having y minus mu in the normal distribution function, we'll substitute mu by the model itself. Okay, f of x and phi. Because we said that we will predict mu, right? Which means that the output of the model is mu. So mu is actually equal to the output of the model, which is f of x and phi. Okay? Type. Is that the loss function? How can we make this a loss function? Take the negative log and multiply and do the sum over all the training examples. Okay? And that's what we will do here. Okay? So this is the likelihood function. Take the log and the negative. Okay, and now this is the loss function. So if we make it on the normal distribution that we saw in the previous slide, then this is because this is normal distribution now, right? So we know the expression of the normal distribution, and we just plug it back here. So this is now the loss function, the original loss function for that problem. Okay, type. Notice something. This is yi, not y. Huh? Yeah, because for this is summation over what? Over the training examples, right? Not over the possible outputs. Okay, not over the possible outputs. This is a summation. It was product before, right? Before we take the log. Okay, it was this now summation over all training examples. For every training example, xi, we have yi, right? In the training examples, we want to see the probability of that yi. That's why we have here yi. Okay, so for every I, we have yi. We want to compute. This is the probability of seeing yi. This is the probability that the model assigns to the correct answer. Okay, this one. Oops, sorry. No. Where is the probability that the model assigned to the correct answer? It's the likelihood probability, right? Where is it? Yes, here, this one. This is the probability, right? This is exactly the normal distribution, the probability density function of the normal distribution. That's the probability, and when we set y to yi, that's the probability of the observed output. That's the probability of the correct answer. Okay, we take the log of it, sum over all training examples, and add the negative. But what if we forgot to put this negative? Now we will minimize we'll get a bad model. Okay, we will minimize something that's good. Okay, so that will give us a bad model, not a good model. Okay, any questions so far? Right. Now let's try to simplify this. That looks really complex, right? Let's try to simplify it. So this is again the negative, like this is where's the loss function? The whole thing, right? From here to here. That's the log function. Not the log function, the loss function. Okay. Type. So we want to find phi that minimize this. Type. Now you see log of product, right? When we have log of a product, we can convert it to sum. So it will be log this plus log this, right? When we do log e to the power something, then it will remove the log and the e, right? So we'll get something like this. It will be log this is this part, okay, plus log the exponential, and then we can remove the log and the exponential, right? So we can remove these, right? So now it is simplified, but still it's exactly the same, right? We didn't do any approximation here. That's not approximation, right? This is just mathematical manipulation. Okay, log of a product is sum of the logs, and then log of e to the power x is x. Okay. Okay. Now we reached this, right? We reached this, right? Right. Now look at this part. Is that, remember that we want to find phi that will minimize all of this, right? Right. This part doesn't have any phi. Is that a function of phi? No, right? And we said that the variance is constant. So this part actually is constant. So we can just remove it. We are minimizing constant plus something, right? So we don't care about this constant. So now we do an approximation. Okay? So it's not approximation in terms of the process, but approximation in terms of values. Now we can remove it, and we only focus on the other part. The value, this value is different than this. Yeah, this function is different than this function. But we don't care because we both will give us the same result, which is the same what here? Same parameters. Okay. So minimizing this function is equivalent to minimizing this function with respect to phi. Yes. We just ignore it, ignoring it. Okay, you just cross it. Okay, because we don't need, because this is constant. Okay, it will not change the value of phi. That's the meaning of it. Okay, if we remove this from the equation, it will not affect the value of phi that we will get eventually. Okay, like what we did with log, right? We have a function, we take the log of it. The value will change, but the value of the function will change, but the maximum of both functions will be at the same point. Okay, can we do something similar again to this now? What is it? What is constant? Yeah, 2 sigma square is also constant, right? So multiplying or dividing by a constant will not change the value that will give us the maximum. So we also ignore it and reach this. Okay, minus times minus, of course, is positive. So now we have the summation of yi minus f of xi and phi. Did you see that before? What is it? It's the least squares loss function. Okay, so it didn't come from Mars. Okay, but imagine that in the first lecture I gave you all of this. Okay, now it is the least squares. You know it. Okay, of course it was easy to talk about it before without the details, but now I think you know how we got it. Okay, it's not just given; we can get it from this mathematical manipulation. Okay. Any question about this? We could have, by the way, kept this function. Yani all of these functions are all of these equations are equivalent, by the way. They will give us the same model. But the last expression is much simpler. It's easier. Okay? And also easier to understand, right? Now you can understand that this is actually the least squares. We are just minimizing the differences between what? Let's put names here. What is f of xi and phi? That's the mean, the predicted mean, right? And this is the actual output, the ground truth, the correct output. Okay. Questions? No questions? Right. Now let's show the difference between the least squares function and the maximum likelihood function. Can you tell me where is the maximum likelihood function here? Or the log likelihood function? Where is the log likelihood function? Which line? Yeah, this part is the likelihood function, and this part is the log likelihood function. Okay, and with the negative, it is the negative log likelihood. Okay, right. If I compute this, no, this is now. How can I call this, by the way? The loss function. Very good. So this is the original loss function, right? And this is the approximated loss function, right? And this is what we plot here. This is the original negative. Actually, this is the negative log, actually. Okay, because that's how it is calculated here. Okay, so this is the original loss function, which is in one case it's minus 6.57, and this is the simple one, that's the least squares, the simpler expression that we got at the end. Okay, let's see what's the difference between them. Remember this example in the regression, I think first 1 or 2 lectures. This is the model that we trained, the green line, and for this point, is the model doing good job or bad job? Good job, right? Why? Because the difference is very small, right? This difference is very small. Okay, let's see that when we see it from the original loss function, how it will look like. Okay, this is the same line, same green line. Okay, and the same point here, this one. Okay, what's happening here? Instead of predicting one point here we are not predicting one point, we are predicting a probability distribution, right? A probability distribution. Where is the probability distribution here? This one. Okay, this one. Okay, type. When we are talking about yi, the probability of yi, remember this is probability of yi, right? See here? Is it the orange dotted line or the green dotted line? Yi. Is it the orange or the green? The orange. Because this is the orange point is the actual output, not the actual output, the correct output. Okay, the correct output. This is the predicted. Okay, so the model predicted the distribution to be like that, and assigned the value to the correct one. That is it far from the maximum? No, not far. Okay, not far. So this is relatively high probability to the correct answer. So it's not very bad. Okay, how about here? In this case, also not very bad, right? Because the model, instead of predicting this to be the correct answer, predicting this. So again, this probability, a probability of yi, is not very bad. Okay, now look at these two examples. Okay, forget about the left side. Let's focus on the right side. Okay, on the right side, where is the probability of yi here? This one is very small, right? Very small. So the model for this point predicted a distribution that assigned a very small probability to the correct answer. Okay. So how about this one? Where is you see where's the distribution that the model predicted أصلا? It's this one, right? What is the assigned probability to the correct answer? Almost zero. Almost zero. So of course this is very bad. And that's reflected by the way in the least squares. You see? So the very bad probability here, which is almost zero, is representing the same bad job that is seen in the least squares by the big difference here. So minimizing, I'm telling you, I'm showing you that either you use the original loss function or you use the simplified loss function, which is the least squares, will give us the same thing. It will eventually penalize bad predictions and penalize much less good predictions. Okay, is that clear from this example? Although the values, by the way, are different. Yani, if you compute the loss function here with that model, this is the model, right? The line, the green line. So this model, if we used the least squares as the loss function, which is the simplified version of the original one, we'll get 10.22. Here we get 400. The values are different. No, penalty means the loss function, you can think of it as a penalty function. Whenever you make a mistake, the value would be high. Okay, so yes, here the total loss is very high value, okay, and different from that value. If we get back to the previous example, you will see here the loss is small, and here also relatively it is small also. Okay, although the loss here is computed in different way. So here it's computed from the original loss function without any simplification. This one, of course, is the simplified one, the least squares function. But both eventually will give us the same learned model, weights and biases. Yes. Yes. Okay. Any questions? Now to do inference, what should we do? Let's say that we learned the model, خلاص. Yes, given a test input, I want to get a prediction. What will be the value of the prediction? How can I get the prediction? And I have a model now. Okay, I have a model. Let's say that this is a neural network. Okay, and this is an input. I give an input here, and I want an output from the other side. Okay, I learned all the parameters here. All of these parameters are learned. What do we call these parameters, by the way? What do we call these parameters? Parameters of the model? Phi. So we learned phi already. خلاص. Okay. Now given input. Okay. X. Let's say مثلا x dot. Okay. For x dot, I want to predict a value, actual value that I can use in reality. Okay, the maximum. In this specific case, the highest probability is what? Is the mean, at the mean. It happened that it aligned very well with what the network itself is predicting. We said that the network here is predicting what? The mean, right? Didn't we say that mu is f of x here, right? That means that the network is actually computing the mean. Okay, so we'll just say this is the value, this is the predicted value, because at the mean the normal distribution is assigning the highest probability. Okay, so for inference we will maximize this probability, which is actually what we predicted, which is the mean. Okay, so y hat will be the center of the distribution, mu. Is that clear now? Any questions? You have a question? No? Unfortunately, you don't have? Well, fortunately, you don't have. Okay, good. Huh? Yes. This one? Yes. Again, this is negative log maximum likelihood, okay? Because this is the expression. Yes. Hmm. In for this, I think for this model, now the loss function is computed for the model over all training examples. Yeah, if we compute it, we get this value. You mean the distribution? Okay. Why are we plotting? Yeah, this is of course just to show you. Okay. Why are we plotting the predicted probability distribution centered at this value? No, no. Because the network predicts the mean. The network itself predicts the mean, okay, which is the center of the probability distribution, of the normal distribution. The model doesn't know the actual value, right? Doesn't know the correct value. Okay, so actually this is a very bad prediction because the correct value is getting very small probability in that distribution. But what could be a good prediction? If the model actually predicted this as the mean, okay, in that case the distribution would be something like this. In that case, the probability of this point is very high. Okay, but that didn't happen with that line. Okay, the other one would be something like this. Okay, that the penalty for this value that would be very small. Okay. Any other questions? Is that a hard lecture? It is hard. To me, it's really hard. But I think after we go through the steps one by one, and I hope that it is clear now. Okay, and next time, inshallah, we will here we assume that we have a constant variance. Okay, next time we will see if we don't want to assume the constant variance, then or constant standard deviation, then what we should do. Okay, that's what we will see inshallah next time. Assalamu alaikum wa rahmatullahi wa barakatuh.